Swayam Prabha. Digital India. Educated India.
We will continue today from where we left on static stability. We are talking about longitudinal stick fixed static stability. The criteria for so this is related to stability in pitch, so we can also call it pitch stability. So, if you remember, we said an aircraft to be statically stable in pitch has to have Cm versus alpha curve which has a negative slope. So, this was the criteria for pitch stability. So, change in pitching moment because of a change in angle of attack. A positive change in angle of attack should automatically result in a negative change in pitching moment, so that the tendency of the aircraft is to kill that extra angle of attack. So, this was the criterion from which we, because this pitching moment expression for pitching moment is Q into S to C bar into Cm. Cm is pitching moment coefficient. We also said that this is equivalent to everything else being constant and positive here. So, we are checking the static stability in pitch at a particular trim condition, and this is the criteria. So, dCm over d alpha should be less than 0, and this is also equivalent to saying dCm over d alpha Cl is less than 0. So, in short form is this is dCm alpha. So, what we said is in order to fly the aircraft stable and at positive trim angle of attack, the aircraft must also have Cm naught, which is pitching moment at alpha equal to 0, which is positive. So, these are the two criteria which an aircraft, two features which an aircraft must possess. And what we want to do now is we want to look at how different components of aircraft contribute to these two parameters. So, we will look at contributions from different component one by one. So, let us first look at what is wing. Is the main component of an aircraft other than the fuselage. let us look at we will later on also look at the contribution coming from the fuselage. Let us first start to look at the wing contribution. So, we define some axes. So, here this line is the reference line, which is called fuselage. So, our idea is to look at this derivative, sign of this derivative due to different components. So, this line is the fuselage reference line, which you can obtain by joining the center line of fuselage different sections, and let us say this is our a section of the wing. So, wing section. The chord line of this wing section is this. Which is making an angle IW with the fuselage reference line. IW is known as wing incidence. So, all angles we are measuring with respect to the fuselage reference line for the aircraft. The angle of attack of the aircraft is with respect to this fuselage reference line, which we can call alpha FRL, or we can drop this FRL and simply write this as alpha, which is for the whole aircraft. So, alpha is the angle of attack of the aircraft, which is measured with respect to the fuselage reference line. The total angle of attack of this section, so V is the relative wind speed coming onto the aircraft, and the angle of attack that this wing section is seeing is alpha W, which is equal to alpha plus IW. So, finally, we want to write down an expression for this moment, pitching moment m. So, we have to look at the forces and the distances, distance of the point where the forces are acting from the CG. So, we will define CG somewhere here to start with, and we take the aerodynamic center of the wing at quarter chord in this simple formulation. So, dW is the drag due to the wing, and LW is the lift created at the wing. In this formulation, or in general, the distances on the aircraft are measured with respect to the wing leading edge, as far as the static stability analysis is concerned. So, this point is the wing leading edge, and distance of the aerodynamic center of the wing from this leading edge is x AC W. We also define the distance of the CG from this. The leading edge, which is xCG. So, other than these two forces, if the, and we are saying that the aerodynamic center is lying at the quarter chord. So, if the wing section is not symmetric, wing airfoil section, then we know that the center of pressure will lie slightly off this aerodynamic center, which is at the quarter chord in this, or let's not assume that. So, we will not assume that this aerodynamic center of the wing is lying at the quarter chord. So, what for symmetric airfoil, the aerodynamic center is at the quarter chord, but for any cambered airfoil section, the distance between the aerodynamic center and the center of pressure is a non-zero value, because of which there is a moment created about the aerodynamic center, and that is MAC W. We will also look at the vertical distances. So, in this case, the vertical distance of the CG from the reference line is ZCG, and the height of the aerodynamic center from the fuselage reference line is ZACW. Let us try to write down the expression for moment now. So, moment about the center of gravity, the pitching moment about center of gravity is equal to MAC W, which is the residual moment, and the moments coming because of the lift and drag forces. So, plus LW into the sine component into ZAC W minus dW cos IW into Z CG minus ZS. So, this distance. So, drag is acting in this direction, it is giving a pitching down moment, that is why this negative sign here. The cosine component of LW is acting in the vertically up direction and is giving a pitching up moment about the CG, and similarly this component sine component of LW is also going to give a pitch up moment. So, that is why these positive signs here, and the final one is the sine component of this drag and this is equal to, so sum of all the moments, sum of the pitching moments due to all components of forces here is equal to m. This m is about the CG. Now, we can expand this equality relation. So, mCg is half rho v squared S into C bar into Cm Cg. We can drop this Cg if, because we are always taking moments about the Cg. So, wherever we do not need it, we will drop that Cg. Here this moment is about the aerodynamic center of the wing. So, we will keep that as Cm ACW. Rho is the density, V is the speed, S is the wing planform area, which is taken as the reference area. C bar is the mean aerodynamic chord. So, let us try to first expand this and then look at what we are getting from here. So, LW is half rho v squared S CL W cos alpha minus alpha W minus IW So, that now with this expression we can write down what is the expression for the pitching moment coefficient, so non-dimensionalized form. So, Cm is Cm ACW plus CLW cos Now, this is the complete expression. If you have all the distances which are significant and all the numbers which are significant, we have to include them, but here for simplifications let's assume that the angles, this angle is small, which is perfectly a valid approximation or assumption, because this we are talking about the pre-stall conditions of flight. So, alpha is a small angle, and if you use this assumption, then let us also make another assumption, and that is, let us assume that the lift created at the wing is much larger than the drag, which is also a valid assumption. Another assumption that one can have, only to look at the simpler form, is that this distance is small. But in general, if these are not valid, then we have to retain all the terms as they are in that equation. So, let us make these assumptions. So, these are the assumptions that we are making to simplify that expression for Cm. Okay. So, because of my assumption, this is equal to 1. This is a small number multiplied with a small number. So, this is further small, which can be neglected. So, we are assuming that this angle is small and this distance is also small. So, that this whole term is much smaller as compared to other terms. So, we can neglect this term. Similarly, here we are assuming that the CDW is very small and this distance is also small, then we can, so small compared to the largest number here. Similarly, CDW and this angle alpha W minus IW both are small, so we can also neglect this term. So, what we get is Cm, now after using these assumptions, Cm equal to Cm AC W plus CLW into XCG minus X ACW over C bar. Let us also try to include the effect of camber. So, the CLW is CL naught W plus CL alpha W into alpha W So, now there is one term which is depending upon the angle of attack, the other one which is not depending upon angle of attack. So, let us try to separate them. So, AW is the lift curve slope of the wing. Into alpha W to XCG minus XACW over C bar. So, this is the expression for the total pitching moment coefficient, and what we want to do is we want to see if they are satisfying these two criteria or not. So, let us try to write down expressions for Cm naught and Cm alpha from here. The expression for Cm naught is Cm ACW plus and Cm alpha is, now we take the derivative of this expression for Cm with respect to the angle of attack. What we get is this. So, clearly for Cm alpha to be less than 0 for this kind of configuration where we have nothing else on the aircraft but the wing, XCG must lie ahead of the x, the location of the aerodynamic center. So, CG must lie before the aerodynamic center for stability. So, what it says is for static stability in pitch for a wing alone configuration, CG must lie ahead of the aerodynamic center of the wing. This is for stability. Now, let us look at what is happening to Cm naught. So, the expression 2 results in this conclusion. The expression 1 for Cm naught. Let us look at that. So, this quantity has to be negative because we have to ensure stability. So, this is negative and what we want is Cm naught must be positive. So, Cm naught positive is the condition to fly the aircraft as positive angle of attack, and which we would want for several reasons, because negative angle of attack is going to result in negative lift. So, let us look at now what is happening here. So, this term is negative. Now, if I have a positively cambered wing, then a positively cambered wing will result in CL naught which is positive. So, CL naught positive. So, this quantity is positive for a positively cambered wing, which generally we would want to have. These are resulting in Cm naught which is negative. From this term. For positively cambered airfoil, this term is also negative. So, for positively, I can say from here that for positively cambered wing, Cm naught is negative. But if we look at a negatively cambered wing, then this term is negative, Cl naught W so positively cambered wing sections, and this is negatively cambered wing section. Cl naught is negative here. So, if we use a negative camber for the wing, then we can make this Cm naught positive. Now, this is working to our advantage, but disadvantage here is, so we are by choosing a negatively cambered wing, we are satisfying the conditions for flying positive trim angle of attack, and also we are satisfying the conditions for static stability and pitch. But you see this portion of course there is a loss of lift overall, and also this portion of the angle of attack for which the lift coefficient is negative. Negatively cambered wing results in loss in CL max, which is clear from here. So, in the case of positively cambered wing, CL max is at this point, and for the negatively cambered wing, the CL max is far below. So, there is a loss in CL max which will affect the performance of the aircraft. So, in general, if we do not use anything else, for example, we will add some more components here. In a normal aircraft, we will see their components like tail attached to a wing, or tail surface usually on the aircraft behind the wing. For this configuration, the wing alone flying configuration of aircraft, you have to have negatively cambered wing for this Cm naught to be positive, and we are seeing here that if we use that, then what we see is a drop in CL max. This drop in CL max can be reduced if we use what is known as an airfoil section which is having a reflex trailing edge. So, in this case the airfoil or wing section is not negatively cambered for all chord portion, it is only negatively cambered for a small portion of the wing, and it looks something like this. So, this is the wing section with reflex trailing edge. This results in less drop in CL max, and it also gives us Cm naught which is positive. A normal aircraft will come equipped with a horizontal tail which will provide extra stability to the aircraft and pitch, and we are going to look at the contribution to Cm naught and Cm alpha coming from the tail in the next class.